Long before Earth became a blue world filled with oceans, before mountains rose above the sea, before the first living cell appeared, there was already a giant growing in the darkness around the young sun. A world unlike any other. A planet so enormous that every other planet in the solar system would eventually feel its pull. For billions of years, it has silently shaped the paths of comets, redirected asteroids, disturbed entire families of worlds, and perhaps even determined whether life on Earth would ever have a chance to begin. Some scientists call it Earth's greatest protector. Others argue it may also be one of the reasons our planet has faced devastating impacts throughout its history. How can one planet be both a guardian and a threat? The answer lies nearly 778 million kilometers from the Sun, inside a world where winds race faster than hurricanes, where storms larger than Earth have raged for centuries, and where crushing pressures transform ordinary hydrogen into something unlike anything found naturally on our planet. This is Jupiter. Love space, science, and cosmic mysteries? Subscribe to the Cosmic Earth and join the adventure as we explore the greatest wonders of our universe. To understand why Jupiter matters so much, we have to travel back nearly 4.6 billion years to a time before there were planets, before moons, before continents, before life. Our solar system began as a gigantic cloud of gas and dust drifting through a quiet corner of the Milky Way. This cloud, known as the solar nebula, contained mostly hydrogen and helium left behind by older generations of stars. Mixed within it were tiny grains of heavier elements: carbon, silicon, iron, oxygen, the ingredients that would one day become planets, oceans, mountains, and living creatures. Something then disturbed this peaceful cloud. Perhaps the explosion of a nearby supernova, perhaps the shockwave from another passing star. Whatever the cause, gravity began pulling the cloud inward. As it collapsed, it spun faster and faster. The growing rotation flattened the cloud into an enormous disk stretching billions of kilometers across space. At its center, pressure and temperature rose rapidly. Eventually, the young sun was born, but the sun did not consume all of the material around it. A vast spinning disk remained. Inside this protoplanetary disk, countless particles collided, tiny grains stuck together. Pebbles became rocks, rocks became mountain-sized bodies called planetesimals. Over millions of years, gravity transformed chaos into order. Closer to the sun, where temperatures were extremely high, only rock and metal could survive. These regions eventually produced Mercury, Venus, Earth, and Mars. Farther away, the environment was completely different. Beyond what astronomers call the frost line, temperatures became cold enough for water, ammonia, and methane to freeze into solid ice. This changed everything. Suddenly, building planets became much easier. Instead of relying only on rock and metal, growing worlds now had enormous quantities of frozen material available. These icy building blocks accumulated rapidly. One growing world began pulling in material faster than any other. Its gravity strengthened with every passing year. As its core became larger, its ability to attract surrounding gas increased dramatically. Scientists estimate that this young world quickly reached around 10 times the mass of Earth. That number was critical, because once it crossed this threshold, something extraordinary happened. The planet no longer attracted only rocks and ice. It began capturing vast amounts of hydrogen and helium directly from the surrounding nebula. Its atmosphere exploded in size. What had started as a large icy core suddenly transformed into a true gas giant. Within a relatively short period in astronomical terms, Jupiter became the largest planet in the solar system. Its growth was astonishing. If Earth were the size of a grape, Jupiter would be almost as large as a basketball. Its diameter eventually reached nearly 143,000 kilometers. More than 11 Earths could fit side by side across its width. Its volume became so enormous that over 1,300 Earths could fit inside it. And yet, despite its incredible size, Jupiter never became a star. Many people wonder why. After all, it is made mostly of the same hydrogen and helium as the Sun. The answer lies in mass. Stars shine because immense gravity compresses hydrogen until nuclear fusion begins. Fusion releases enormous amounts of energy. It is what powers every star in the universe. But Jupiter simply wasn't massive enough. Although it contains more than twice the mass of all the other planets combined, it still possesses only about 1,000th the mass of the Sun. To ignite sustained fusion, it would have needed roughly 80 times more mass than it has today. Instead of becoming a second sun, Jupiter remained something in between. Neither rocky planet nor star, a giant world of gas, hiding mysteries deep beneath its colorful clouds. Those clouds are the first thing anyone notices. Bands of white, brown, orange, cream, red. From a distance, they appear peaceful, beautiful, almost artistic. But appearances are deceptive. These colorful stripes mark enormous rivers of atmosphere flowing around the planet at incredible speeds. Powerful jet streams circle Jupiter in opposite directions. Some winds exceed 600 kilometers per hour. Unlike Earth, there are no continents to interrupt these winds, no mountains to slow them down. Nothing but endless atmosphere stretching across the planet. Within this restless world, storms can grow to unimaginable sizes. The most famous is the Great Red Spot, a gigantic storm larger than Earth itself. It has been observed continuously for more than 350 years. No storm on Earth has ever survived even a tiny fraction of that time. On Jupiter, storms become part of the planet's identity. Lightning also flashes deep inside its clouds. Some bolts are several times more powerful than those on Earth. Towering clouds rise dozens of kilometers high. Ammonia crystals freeze near the upper atmosphere. Far below, water clouds form under crushing pressure. Still deeper, scientists believe liquid hydrogen dominates the interior. And below that, the pressure becomes so extreme that hydrogen itself changes into an exotic form known as metallic hydrogen. Here, hydrogen no longer behaves like an ordinary gas. Instead, it acts almost like a liquid metal capable of conducting electricity. This strange layer may be responsible for one of Jupiter's most astonishing features, its magnetic field. Jupiter possesses the largest and most powerful planetary magnetic field in the solar system. If it were somehow visible from Earth, it would appear larger than the full moon in our sky, despite being hundreds of millions of kilometers away. This immense magnetic bubble traps enormous numbers of charged particles. It creates intense radiation belts capable of damaging spacecraft electronics. For any future astronauts, they would be among the most dangerous regions anywhere in the solar system. Even approaching Jupiter requires careful planning. NASA's Juno spacecraft survives only because engineers designed it with a heavily shielded titanium vault protecting its most sensitive instruments. Without that protection, its electronics would quickly fail. Yet despite these hostile conditions, Jupiter continues to fascinate scientists, not only because of what it is, but because of what it has done. Its immense gravity reaches far beyond its visible clouds. Invisible, yet constantly at work. Every asteroid drifting nearby, every icy comet falling inward from the outer solar system, every small object wandering through space, must answer to Jupiter's gravitational pull. For billions of years, this silent giant has acted like an invisible architect, sometimes collecting wandering objects, sometimes throwing them away, sometimes redirecting them toward the inner planets, including Earth. Its influence extends across almost every corner of the solar system. Even today, many astronomers believe that if Jupiter had never formed, the solar system we know would look completely different. Mars might be much larger, the asteroid belt might not exist in its present form. Earth's history could have unfolded along an entirely different path. Perhaps life would never have emerged, or perhaps life would have evolved much sooner. No one knows for certain. But one fact is impossible to ignore. Jupiter is not simply another planet orbiting the Sun. It is one of the main reasons the solar system became the place we call home. Yet this is only the beginning of its story, because the giant did not remain where it was born. In the earliest days of the solar system, Jupiter may have started moving, and that single journey could have changed the destiny of every planet that followed. When we look at the solar system today, everything appears calm. The planets follow predictable paths. Mercury races around the Sun. Earth circles once every year. Jupiter completes its enormous orbit every 12 years. It almost feels as though the solar system has always looked this way, as if every planet was born exactly where we see it today. But modern astronomy tells a very different story. The early solar system was not peaceful. It was chaotic, violent, unstable. Worlds were still growing. Asteroids collided constantly. Young planets fought for material. Nothing had settled into permanent orbits. And in the middle of this cosmic construction site, one planet refused to stay still: Jupiter. Today it travels around the Sun at an average distance of nearly 778 million kilometers. For centuries, astronomers assumed it had always occupied that distant orbit. It seemed like the obvious explanation. After all, moving a planet more than 300 times the mass of Earth sounded almost impossible. But over the past few decades, computer simulations began revealing something unexpected. Many of them failed to recreate our solar system unless Jupiter had migrated after its birth. The evidence pointed toward a remarkable possibility. The largest planet in the solar system had once been a traveler. This idea became known as planetary migration. It has transformed the way scientists understand not only our solar system but planetary systems throughout the galaxy. The reason is surprisingly simple. A newborn gas giant does not exist in empty space. When Jupiter formed, it was surrounded by an immense disk of gas and dust. Although that gas was thin by earthly standards, it contained enormous amounts of mass spread across billions of kilometers. As Jupiter orbited the young Sun, its gravity disturbed this surrounding material. The gas pulled on Jupiter. Jupiter pulled back on the gas. These continuous gravitational interactions acted almost like invisible currents in a river. Very slowly, they changed the planet's orbit. Instead of remaining perfectly fixed, Jupiter likely drifted inward toward the Sun. Not quickly, not dramatically over a human lifetime, but over hundreds of thousands of years, the movement became significant. Some models suggest Jupiter may have traveled as close as roughly 1.5 astronomical units from the Sun. That placed it not far beyond the orbit where Mars exists today. If that happened, the consequences were enormous. Every object in its path felt Jupiter's gravity. Countless planetesimals were scattered, some crashed together, others were thrown toward the Sun, many were launched into deep space forever. The inner solar system became a place of constant rearrangement. But Jupiter's journey did not end there. Another giant planet was beginning to form: Saturn. As Saturn grew larger, its own gravitational influence increased. Eventually, the two giants became locked together through a phenomenon called orbital resonance. Their gravitational pulls synchronized in a precise rhythm. Instead of continuing inward, their combined interaction with the surrounding gas reversed the process. Both planets began migrating outward. This remarkable scenario is known as the Grand Tack hypothesis. The name comes from sailing. When a sailboat changes direction by turning through the wind, it performs a maneuver called a tack. According to this hypothesis, Jupiter made a similar turn in space. It moved inward, then changed course and headed back outward. That single reversal may explain some of the greatest mysteries in planetary science. One mystery involves Mars. Compared with Earth and Venus, Mars is surprisingly small. It contains only about 1/10 the mass of Earth. For years, astronomers struggled to understand why. The region where Mars formed should have contained enough material to build a much larger planet, yet somehow that material disappeared. The Grand Tack hypothesis offers an elegant explanation. As Jupiter migrated inward, its gravity swept through the region where Mars was still forming. Much of the available material was either scattered away, captured elsewhere, or thrown toward the Sun. Mars simply ran out of building blocks. Its growth slowed dramatically. The small red planet we see today may be the direct result of Jupiter's ancient journey. Another puzzle lies between Mars and Jupiter, the asteroid belt. At first glance, it appears to be the remains of a planet that never formed. This idea became popular centuries ago, but modern evidence tells a different story. The combined mass of every asteroid in the belt is less than 5% of our Moon's mass. There was never enough material there to build a large planet after Jupiter's migration disrupted the region. Instead, Jupiter's gravity constantly stirred the asteroids. Whenever they tried to gather into larger bodies, their orbits were disturbed. Collisions became too violent. Rather than merging, many objects shattered apart. The asteroid belt became a graveyard of interrupted planet formation. Even today, Jupiter continues to shape it. Certain regions within the belt are strangely empty. These gaps are known as Kirkwood gaps. They occur where an asteroid's orbital period matches a simple ratio with Jupiter's orbit. For example, an asteroid that circles the Sun exactly 3 times, while Jupiter completes one orbit, experiences repeated gravitational tugs. Each pass adds a tiny push. Over millions of years, those pushes accumulate. Eventually, the asteroid's orbit changes dramatically. Some are ejected from the belt. Others are sent toward the inner solar system. Gravity, acting patiently over immense stretches of time, reshapes entire populations of worlds. Jupiter also shepherds thousands of asteroids that share its orbit. These are known as the Trojan asteroids. They travel around the Sun 60 degrees ahead of Jupiter and 60 degrees behind it. These special locations, called Lagrange points, are regions where gravitational forces balance in remarkable ways. Thousands of rocky bodies have remained trapped there for billions of years. They are like ancient fossils from the birth of the solar system. NASA's Lucy mission is exploring several of these Trojans to learn more about the earliest history of planetary formation. Each asteroid may preserve clues from a time before Earth had oceans, before continents, before life itself. But Jupiter's influence reaches even farther. Beyond Neptune lies the Kuiper Belt, a vast collection of icy worlds. Far beyond that, surrounding the solar system like a distant shell, is the enormous Oort cloud. It is thought to contain billions, perhaps trillions, of frozen objects. These icy bodies spend millions of years in deep darkness. Most will never approach the Sun, yet some eventually do. Passing star, galactic tides, and gravitational disturbances can alter their paths. When that happens, many begin falling inward, and sooner or later, they encounter Jupiter. Sometimes, the giant planet captures them. Sometimes, it flings them back into deep space. Sometimes, it redirects them into entirely new orbits. Its gravity acts like a cosmic traffic controller, constantly reorganizing the movement of countless objects across the solar system. This is why astronomers often describe Jupiter as the solar system's architect, not because it built the planets directly, but because its gravity has spent billions of years reshaping nearly everything around it. Even Earth's orbit has remained stable partly because of the delicate gravitational balance established among the giant planets. Without that balance, the solar system might have evolved into something completely different, perhaps unstable, perhaps chaotic, perhaps incapable of supporting long-term habitability. Yet the same force that helped organize the solar system also creates danger. Every time Jupiter changes the path of an asteroid or redirects a distant comet, the outcome is unpredictable. Some objects are safely removed from the inner solar system. Others are sent inward, toward Mars, toward Venus, toward Earth. This dual role has sparked one of the most fascinating debates in modern astronomy. Is Jupiter truly Earth's greatest protector? Or has it quietly been sending some of history's most dangerous visitors in our direction? The answer is far more complicated than scientists once believed, and uncovering that truth means following the paths of comets into the immense gravitational reach of the solar system's most powerful planet. For generations, Jupiter has been known by a remarkable title, Earth's Protector. It is an idea that appears in science books, documentaries, and even conversations among astronomers. The reasoning seems obvious. Jupiter is the largest planet in the solar system. Its gravity is immense. Surely a giant world like this must shield the smaller planets from countless incoming dangers. For many years, this belief seemed almost unquestionable. After all, Jupiter's gravity dominates everything around it. It contains more than twice the mass of every other planet combined. Its gravitational influence stretches millions of kilometers into space. Any wandering object that ventures too close is forced to obey its pull. But space is rarely simple, and gravity, while predictable, does not always produce predictable outcomes. To understand whether Jupiter truly protects Earth, we first have to understand where the danger comes from. The solar system is far from empty. Between the planets drift billions of rocks. Some are no larger than grains of dust. Others are mountains floating through space. Far beyond Neptune, countless icy bodies orbit quietly inside the Kuiper Belt. Even farther away, a distance is almost impossible to imagine, lies the mysterious Oort cloud. Unlike the relatively flat planetary system, the Oort cloud surrounds the Sun in every direction. It forms an enormous spherical shell extending perhaps 100,000 astronomical units from the Sun. If Earth were 1 meter from the Sun, the outer edge of the Oort cloud would be nearly 100 kilometers away. It is one of the largest known structures connected to our solar system. Within this frozen wilderness, billions of ancient comets remain almost unchanged since the solar system formed. Most never move toward the inner planets. They simply orbit in deep darkness, sometimes taking millions of years to complete a single journey around the Sun. But occasionally, something disturbs them. A nearby passing star, the gentle tidal forces created by the Milky Way itself, or the slow accumulation of countless tiny gravitational influences. These disturbances slightly alter a comet's orbit. At first, the change may be almost impossible to detect. But over millions of years, that tiny shift becomes enormous. Eventually, the comet begins falling toward the Sun. As it accelerates, its speed increases dramatically. Some long-period comets race through the inner solar system at more than 70 kilometers every second. That is over 250,000 kilometers per hour. If one of these objects struck Earth, the consequences could be catastrophic. Fortunately, before many of them ever approach our planet, they encounter something else: Jupiter. Because of its enormous mass, Jupiter possesses a vast gravitational sphere of influence. As incoming comets approach, their paths begin to bend. Some swing around the giant planet and continue on altered trajectories. Others lose enough energy to become trapped in shorter orbits around the Sun. These eventually become known as Jupiter family comets. Instead of returning once every few million years, they now revisit the inner solar system every few years or decades. Many famous comets belong to this family. Others are not so fortunate. Jupiter's gravity captures them completely. Over time, they spiral inward. Eventually, they disappear into the planet itself. One extraordinary event allowed humanity to witness this process firsthand. In 1992, astronomers Carolyn and Eugene Shoemaker, working with amateur astronomer David Levy, discovered an unusual comet. It appeared different from anything seen before. Instead of a single bright nucleus, it looked like a string of glowing fragments stretched across space. The object became known as Shoemaker-Levy 9. Scientists soon realized something astonishing. The comet had already passed extremely close to Jupiter. During that encounter, the planet's immense tidal forces had literally torn it apart. Instead of one comet, there were more than 20 separate fragments, each following nearly the same path. Calculations predicted something extraordinary. 2 years later, those fragments would collide with Jupiter itself. In July 1994, the world watched. One fragment after another slammed into the giant planet. The explosions were unlike anything ever observed in the solar system. Some released energy equivalent to millions of megatons of TNT. Dark scars larger than Earth appeared high in Jupiter's atmosphere. For weeks, those impact marks remained visible through telescopes. It was the first time humanity had directly witnessed two major objects colliding beyond Earth. The event became one of the greatest demonstrations of Jupiter's enormous gravitational influence. Many people looked at those impacts and reached a simple conclusion. If Jupiter had not been there, perhaps those fragments would have continued toward the inner solar system. Perhaps one day, they might have crossed Earth's orbit instead. In that sense, Jupiter appeared to act as a gigantic cosmic shield, and there is truth to that idea. Computer simulations show that Jupiter does remove many dangerous objects from the solar system. Some are ejected completely into interstellar space. Others crash into the giant planet. Many never reach Earth's neighborhood at all. Without Jupiter, our planet might experience more impacts from certain populations of long-period comets. That sounds reassuring. But there is another side to the story. Gravity does not distinguish between protection and redirection. Whenever Jupiter interacts with an incoming object, it changes that object's orbit. Sometimes, the new orbit moves the object safely away from Earth. Other times, it does exactly the opposite. Imagine rolling a ball across a smooth floor. Place a heavy bowling ball in its path. The smaller ball will change direction depending on how closely it passes. Gravity works in much the same way. Jupiter can act like a giant slingshot. Instead of stopping a comet, it may accelerate it. Instead of ejecting it from the solar system, it may send it inward toward the rocky planets. Astronomers have discovered many near-Earth objects whose distant pasts appear connected to Jupiter's gravitational influence. Some asteroids originally lived peacefully inside the main asteroid belt. Repeated encounters with Jupiter slowly altered their orbits. Each pass changed their path only slightly. But over millions of years, those tiny changes accumulated. Eventually, their new orbits crossed Earth's. The same process affects some comets. Jupiter transforms distant frozen bodies into regular visitors of the inner solar system. Some remain harmless, others become potential hazards. This surprising realization forced scientists to rethink the old picture of Jupiter as a perfect guardian. Modern computer simulations paint a far more complicated image. In some scenarios, Jupiter reduces the number of dangerous impacts. In others, it actually increases them. The outcome depends on the type of object being studied. Long-period comets, short-period comets, asteroids. Each responds differently to Jupiter's gravity. There is no single answer. Instead, Jupiter acts as both a shield and a source of danger, a planet capable of protecting Earth, while simultaneously creating entirely new threats. This delicate balance may have influenced our planet for billions of years. Every extinction event, every major impact, every close encounter, somewhere in the background, Jupiter's gravity may have played a role. Sometimes obvious, sometimes hidden, sometimes impossible to trace with certainty. Yet one thing is undeniable. Earth has survived countless cosmic dangers since life first appeared. Many of those dangers never reached us, others did. The story of our planet is written not only by oceans, continents, and evolution, but also by invisible gravitational forces acting across hundreds of millions of kilometers. Jupiter has always been part of that story, not as a silent observer, but as an active participant, a giant whose gravity never rests, a world constantly reshaping the architecture of the solar system. But if Jupiter's influence reaches so far, then another question becomes impossible to ignore. What would happen if this enormous planet simply disappeared? Would Earth become safer? Or would the solar system itself begin to fall apart? Imagine looking up at the night sky and knowing that the largest planet in the solar system had suddenly vanished. No explosion, no warning, no trace. One moment, Jupiter is there, the next, it is gone. At first, nothing on Earth would seem different. The sun would still rise, the moon would still orbit our planet, the familiar constellations would remain unchanged, life would continue as usual, but deep in space, the consequences would begin almost immediately, because Jupiter is not just another planet, it is a gravitational giant. For more than 4.5 billion years, its immense gravity has helped maintain a delicate balance throughout the solar system. Remove that balance, and the architecture of our planetary neighborhood slowly begins to change. The first effects would appear among the countless small objects scattered between the planets. The asteroid belt, located between Mars and the giant planets, is constantly shaped by Jupiter's gravity. Every asteroid follows an orbit influenced by the giant planet. Some remain stable for billions of years, others are slowly pushed into new paths. Without Jupiter, those invisible gravitational patterns would disappear. The famous Kirkwood gaps, empty regions carved by Jupiter's repeated gravitational tugs, would gradually begin to fill. Asteroids that had once been trapped in predictable resonances would drift into entirely new orbits. Some collisions inside the asteroid belt might actually decrease. Others could become more common. The entire region would slowly reorganize itself, but the asteroid belt is only part of the story. Far beyond Neptune, millions of icy bodies quietly circle the Sun. Many of them are influenced by Jupiter long before they ever approach the inner solar system. Today, Jupiter often acts like a massive gatekeeper. It captures some comets, ejects others, deflects many away from Earth. Without that giant barrier, more long-period comets from the distant Oort cloud could travel deeper into the solar system. Some computer models suggest that Earth might eventually experience a greater number of comet impacts. But at the same time, another source of danger would disappear. Jupiter would no longer redirect certain asteroids toward the inner planets. The giant gravitational slingshot would be gone. Instead of constantly reshaping nearby objects, space would become quieter in some ways and more dangerous in others. This is why scientists still debate Jupiter's true role. Its absence would not simply make Earth safer or more dangerous. It would completely change the balance of impact risks. Gravity rarely creates simple answers. The giant planets themselves would also feel the difference. Saturn, Uranus, and Neptune constantly interact with Jupiter through gravity. Although separated by enormous distances, they subtly influence one another over millions of years. Without Jupiter, their orbits would slowly evolve. The changes would be tiny at first, almost impossible to notice. But over hundreds of millions, or billions of years, those tiny differences could accumulate. Planetary systems are surprisingly sensitive. Even small gravitational changes, repeated endlessly, can eventually produce dramatic results. Fortunately, Earth's orbit around the Sun would remain relatively stable for a very long time. The Sun contains almost all the mass in the solar system. Its gravity overwhelmingly controls Earth's motion. Jupiter is influential, but it does not hold Earth in orbit. Our year would still last about 365 days. The seasons would continue. Life would not suddenly collapse because Jupiter disappeared. Yet Earth's long-term future might slowly become less predictable. The giant planets help distribute gravitational forces throughout the solar system. Their interactions contribute to the remarkable stability that has allowed life to evolve over billions of years. Without Jupiter, future planetary evolution could gradually follow a different path, perhaps only slightly, perhaps dramatically. No simulation can predict every possibility. But Jupiter's importance extends beyond gravity alone. It is also a natural laboratory. Everything about the giant planet challenges our understanding of physics. Its atmosphere contains layers unlike anything on Earth. Its clouds stretch thousands of kilometers deep. There is no solid surface where a spacecraft could safely land. As scientists probe deeper, pressure rises rapidly. Hydrogen gas becomes liquid. Still deeper, the pressure reaches millions of times greater than Earth's atmosphere. Here, ordinary hydrogen transforms into metallic hydrogen. This strange material behaves almost like molten metal. It conducts electricity with remarkable efficiency. Scientists believe enormous electrical currents flowing through this layer, generate Jupiter's extraordinary magnetic field. That magnetic field is truly colossal. It extends millions of kilometers into space. On the side facing the Sun, the solar wind compresses it. On the opposite side, the magnetosphere stretches so far that it reaches beyond Saturn's orbit at times. No other planetary magnetic field comes close in size. Within this invisible magnetic bubble, charged particles become trapped at tremendous energies. Radiation levels near Jupiter are so intense that an unprotected human would receive a lethal dose in a very short time. Even robotic spacecraft struggle to survive. NASA's Juno mission repeatedly dives through these dangerous regions. Each close pass exposes the spacecraft to powerful radiation capable of damaging sensitive electronics. To survive, its instruments are protected inside a titanium radiation vault. Despite these harsh conditions, Juno has transformed our understanding of Jupiter. It discovered powerful cyclones surrounding both poles. It revealed that Jupiter's weather extends far deeper than scientists expected. Its instruments detected enormous lightning storms, towering atmospheric structures, and surprisingly complex patterns hidden beneath the colorful cloud tops. Each discovery reminds us that Jupiter is far more dynamic than earlier generations imagined. Yet perhaps the greatest surprise lies not within Jupiter itself, but around it. Orbiting the giant planet are 95 known moons, each with its own unique story. Some are tiny captured asteroids. Others are worlds larger than planets once known to ancient astronomers. Among them, 4 stand above all the others. The Galilean moons, discovered by Galileo Galilei in 1610. Their discovery changed humanity forever. For the first time, people saw objects orbiting something other than Earth. The old belief that everything revolved around our planet began to collapse. Modern exploration has revealed these moons to be extraordinary worlds. Io, the most volcanically active body in the solar system. Its surface is constantly reshaped by eruptions powered by Jupiter's immense tidal forces. Europa, a frozen moon hiding a global ocean beneath its icy crust. Many scientists consider it one of the most promising places to search for extraterrestrial life. Ganymede, the largest moon in the solar system, even larger than the planet Mercury. Remarkably, it possesses its own magnetic field, something no other known moon can claim. And Callisto, an ancient world covered in impact craters, preserving a record of the violent history of the early solar system. Together, these moons form a miniature planetary system, orbiting a giant that almost resembles a small solar system of its own. They remind us that Jupiter is far more than a single planet. It is an entire family of worlds, each one revealing another chapter in the story of planetary evolution. And today, humanity is preparing to return. NASA's Europa Clipper spacecraft and the European Space Agency's JUICE mission are traveling toward Jupiter. Their goal is not simply to study the giant planet, it is to investigate whether some of its moons could support life. If oceans exist beneath Europa's frozen shell, if the chemistry is right, if energy sources are present, then one of Jupiter's moons could become the first place beyond Earth where humanity discovers living organisms. It would be one of the greatest scientific discoveries in history. But before we search for life around Jupiter, we must answer one final question. How can a planet so hostile, so violent, and so deadly also become one of the greatest places in the solar system to search for life? That extraordinary contradiction may be Jupiter's greatest secret. For thousands of years, Jupiter was nothing more than a brilliant point of light in the night sky. Ancient civilizations gave it names. They associated it with kings, storms, and powerful gods. The Romans named it after Jupiter, the ruler of their gods. The Greeks knew it as Zeus. In Babylon, represented Marduk. Across different cultures, people sensed that this unusually bright object was somehow special. They had no telescopes, no spacecraft, no understanding of gravity. Yet they instinctively connected the brightest planet in the sky with power. Centuries later, science would reveal just how accurate that intuition had been. Jupiter truly is the king of the solar system. Not because it shines the brightest, not because it is the largest, but because almost everything in our planetary neighborhood has, at some point, felt its influence. Its gravity has shaped planets, redirected asteroids, captured moons, disturbed comets, and quietly helped determine the environment in which Earth evolved. Without Jupiter, our solar system would not be the one we know today. Whether life would still exist, no one can say with certainty. Perhaps Earth would have endured far more catastrophic impacts, perhaps fewer. Perhaps Mars would have grown into a second Earth. Perhaps the asteroid belt would have become another planet. The truth is, every major object in the solar system is connected through gravity. Remove one giant piece, and the entire system slowly changes. That is one of the greatest lessons Jupiter teaches us. Nothing in the universe exists in complete isolation. Every planet, every moon, every asteroid, every comet is part of an intricate gravitational dance that has continued for billions of years, and Jupiter leads much of that dance. Yet despite everything we have learned, the giant planet still keeps many secrets. Scientists are still trying to answer one of the biggest questions: what exactly lies at Jupiter's center? For decades, researchers believed a massive rocky core must exist beneath the layers of metallic hydrogen, but data from NASA's Juno spacecraft challenged that idea. Instead of a small, dense core, Jupiter may possess what scientists call a diluted or fuzzy core. Rather than having a clear boundary, heavy elements appear to be mixed throughout a large portion of the planet's interior. This suggests that sometime early in its history, Jupiter may have experienced an enormous collision, perhaps with a young planetary embryo several times the mass of Earth. Such an impact could have disrupted its original core, mixing heavy materials into the surrounding layers. If true, the largest planet in the solar system still carries the scars of an ancient catastrophe hidden beneath thousands of kilometers of clouds. Its atmosphere also continues to surprise researchers. The colorful bands that wrap around the planet are not permanent. Storms grow, storms disappear, jet streams shift, cloud chemistry changes over time. Even the famous Great Red Spot, once thought to be eternal, is slowly shrinking. When astronomers first measured it in the 19th century, it was nearly twice as wide as it is today. No one knows exactly how long it will survive. One day, the solar system's most famous storm may simply fade away. Jupiter also produces some of the most spectacular auroras ever observed. Near its poles, curtains of glowing light shine continuously. Unlike Earth's aurora, which depend mainly on solar activity, Jupiter's are powered not only by the sun, but also by its own immense magnetic field, and by material ejected from its volcanic moon, Io. Sulfur and oxygen particles, blasted into space by Io, become trapped inside Jupiter's magnetosphere. As they spiral toward the poles, they create brilliant ultraviolet auroras hundreds of times more energetic than those on Earth. The giant planet is not just influencing the space around it, its moons are actively feeding energy back into the system. Together, Jupiter and its satellites behave like a connected planetary engine. This relationship has become one of the most fascinating natural laboratories in the solar system, and it may help answer a question that humanity has asked for generations. Are we alone? Beneath Europa's frozen crust, scientists believe a global ocean may contain more liquid water than all of Earth's oceans combined. The ocean is hidden beneath an ice shell that may be several kilometers thick. Tidal forces generated by Jupiter constantly squeeze the moon, producing heat deep inside. That heat may keep the ocean liquid despite the extreme cold of space. If rocky seafloors, chemical nutrients, and long-term energy sources all exist together, then Europa possesses several of the ingredients that life on Earth required to begin. No one knows whether life is actually there. It may be nothing more than sterile water beneath frozen ice. Or it could contain simple microbial organisms that have evolved in darkness for billions of years. Even the discovery of a single microscopic cell would forever change humanity's understanding of life in the universe. It would prove that biology is not unique to Earth. That possibility alone has transformed Europa into one of the most important destinations in planetary exploration. The coming decades may finally provide answers. NASA's Europa Clipper mission is designed to study Europa in extraordinary detail. Rather than landing, It will perform dozens of close flybys. Its instruments will examine the moon's icy shell, its hidden ocean, its surface chemistry, and possible plumes of water escaping into space. Meanwhile, the European Space Agency's JUICE mission is exploring Jupiter and several of its largest moons. It will investigate Ganymede, Callisto, and Europa before eventually entering orbit around Ganymede itself. For the first time, humanity will study an entire miniature planetary system with unprecedented precision. These missions are not searching only for life, they are helping us understand how giant planets influence the formation of worlds throughout the universe. Thousands of exoplanets discovered around distant stars include enormous gas giants similar to Jupiter. Some orbit extremely close to their stars, others travel along highly elliptical paths. Many appear to have migrated across their planetary systems, just as Jupiter may have done billions of years ago. By understanding our own giant planet, astronomers gain insight into countless other solar systems scattered across the Milky Way. In many ways, Jupiter has become a bridge between our solar system and every planetary system beyond it, perhaps somewhere around another distant star. Another giant planet protects a small blue world, or perhaps it threatens that world in ways remarkably similar to Jupiter. The story we have followed is not only about one planet, it is about balance, creation and destruction, protection and danger, order and chaos. Jupiter embodies all of these contradictions. Its gravity has prevented countless objects from reaching Earth. Its gravity has also redirected others toward the inner solar system. It helped shape the planets, yet prevented some worlds from ever fully forming. It powers deadly radiation belts, while orbiting moons that may harbor the conditions necessary for life. Few places in the universe illustrate nature's complexity so clearly. The more we study Jupiter, the less it resembles a simple gas giant. Instead, it becomes the invisible architect of our cosmic neighborhood, a silent force that has influenced nearly every chapter of Earth's history without ever touching our world directly. Every sunrise, every forest, every ocean, every living creature exists within a solar system whose history was shaped, in part, by this distant giant. That realization changes the way we see our place in the universe. Earth is not an isolated island drifting through space. It is one member of a vast gravitational family, a family in which every world leaves its mark on the others, and among them all, none has left a deeper mark than Jupiter, the giant that has protected Earth, threatened Earth, and quietly helped write the story of the only known world where life has flourished. Its storms still rage, its magnetic field still stretches across millions of kilometers, its moons continue to orbit in silent harmony. And somewhere beneath those endless clouds, the greatest secrets of the solar system may still be waiting for us to discover.